A journey to the center of the Earth is only 4,000 kilometers long, but with our best technology, we've barely scratched the first 0.4% of that distance. The deepest humans have ever drilled is the Kola super deep borehole in Russia, about 12 kilometers down. That's impressive for engineering, but compared to Earth's radius of roughly 6,371 kilometers, it's thinner than a single coat of paint on a globe. Everything we think we know about the rest of Earth's interior, the vast mantle, the liquid outer core, the solid inner core, comes from indirect evidence. From listening to how earthquakes shake the planet, from how gravity and magnetic fields behave, and from how materials respond to extreme pressure in high-tech laboratories. So when we say crust, mantle, and core, those aren't just cartoon layers on a textbook diagram. They're carefully inferred, quantitatively constrained structures, each with its own physics and personality. Let's start from the outside in. The crust is the solid shell we live on, but solid doesn't mean uniform. There are actually two main types of crust, continental and oceanic. Continental crust is thicker, on average about 35 kilometers, and under big mountain ranges, it can reach 60 to 70 kilometers deep. It's made mostly of relatively light, silica-rich rocks like granite. Oceanic crust is thinner, usually only 5 to 10 kilometers thick, and denser, built mainly from basalt, which contains more iron than magnesium. If you imagine Earth as an apple, the crust would be much thinner than the apple's skin. In some places, it's more like a layer of dust on that skin. This contrast in thickness and density matters. Continental crust floats higher on the underlying material, like a thick piece of styrofoam riding above water, while oceanic crust sits lower, like a thinner plank of wood. This buoyancy difference is why continents rise above sea level and oceans occupy deep basins. It also shapes plate tectonics, the slow motion of rigid plates of crust and uppermost mantles sliding and colliding over geological time. When dense oceanic crust meets lighter continental crust at a subduction zone, the oceanic plate tends to sink, or subduct, back into the mantle. That recycling process not only builds mountain chains and fuels volcanoes, it's one of the ways material from the crust returns into Earth's interior and interacts with the layer below, the mantle. Beneath the crust, we hit the mantle, and this is where our intuitive sense of rock starts to break down. The mantle is not a pool of molten lava. It is mostly solid rock, but it is rock under such high temperature and pressure that it behaves like an incredibly slow-moving, high-viscosity fluid over long time scales. Think of the difference between glass in a window, which seems rigid but can creep under gravity over centuries, and honey flowing in a jar. The mantle extends from the base of the crust down to about 2,900 kilometers depth. That means it occupies about 84% of Earth's volume. If Earth were a chocolate truffle, the mantle would be the gigantic bulk of the filling, with the crust just a thin outer shell and the core a dense center. Geophysicists usually divide the mantle into an upper and lower section with a transition zone in between. The upper mantle, from about 35 or so kilometers down to roughly 410 kilometers, includes the lithospheric mantle, rigid and tied to the plates. And below that, a region called the asthenosphere. The asthenosphere is not liquid, but it's mechanically weaker and more ductile. It's hot enough and under enough pressure that its rocks, mainly peridotite rich in olivine and pyroxene minerals, can slowly flow. We know this not just from theory, but from seismic waves. When earthquakes send vibrations through Earth, these seismic waves speed up, slow down, and bend depending on the stiffness and density of the material they pass through. By measuring how long it takes different types of waves to reach seismometers all over the world, scientists can tomographically image the interior, much like a CT scan images your body. The asthenosphere shows up as a zone where seismic waves travel more slowly, meaning it's softer and partially molten in places. Deeper down, between about 410 and 660 kilometers, lies the mantle transition zone. Here, the pressure is so intense that the crystal structures of mantle minerals actually change. For example, olivine, a common upper mantle mineral, rearranges its atoms into denser forms, like wadsleyite and ringwoodite. This happens at fairly sharp depths, and those boundaries produce seismic reflections and refractions, echoes in the data, that let us pin down where they are. Then, below about 660 kilometers, we enter the lower mantle, extending to 2,900 kilometers depth. In the lower mantle, the chemistry is broadly similar, still dominated by silicate minerals, but the structure again changes as pressure increases to hundreds of thousands of times atmospheric pressure. New mineral phases, like bridgmanite, appear. Bridgmanite is currently thought to be the most abundant mineral on Earth by volume, yet no human has ever seen it in its natural habitat. It was first identified in shock experiments and then in tiny grains within meteorites, because it becomes unstable at the lower pressures near the surface. So how does the mantle move? If it's mostly solid, the key is convection driven by heat. Earth's interior is hot for three main reasons. First, leftover heat from a planet's formation, from countless collisions of planetesimals, and the energy released as material differentiated and heavy metals sank inward. Second, radioactive decay of isotopes like uranium-238, thorium-232, and potassium-40, which steadily release heat as their nuclei spontaneously transform over billions of years. And third, latent heat released as the inner core slowly crystallizes from the outer core. This internal heat tries to escape toward the surface. Hotter, slightly less dense mantle material tends to rise, while cooler, denser material near the surface tends to sink, setting up extremely slow convection currents. These flows happen at rates of a few centimeters per year, about as fast as your fingernails grow. But over tens to hundreds of millions of years, they reshape continents and build entire mountain ranges. Convection in the mantle is the engine behind plate tectonics on the surface. At about 2,900 kilometers down, seismic waves reveal a dramatic change. One particular type of seismic wave, called an S wave, can only travel through solids. Another type, called a P wave, can travel through both solids and liquids. When big earthquakes occur, we can track how P and S waves pass through the planet. S waves that try to go deep into the planet simply vanish beyond a certain depth, while P waves suddenly slow and bend. This tells us that at that boundary, known as the core mantle boundary, or CMB, we encounter a liquid layer, the outer core. The outer core extends from about 2,900 to 5,150 kilometers in depth. It is mostly a molten alloy of iron and nickel, with a bit of lighter elements like sulfur, oxygen, or silicon mixed in. Temperatures at the top of the outer core are estimated to be around 3,500 to 4,000 degrees Celsius, increasing to perhaps 5,000 or more degrees near the center. The pressure there is about 1.3 million times the air pressure at sea level. Within this electrically conducting liquid metal shell, something extraordinary happens: the geodynamo. As the outer core convects, with hotter, less dense fluid rising, and cooler, denser fluid sinking, and as Earth rotates, these flows twist and shear. Moving conductive fluid in the presence of existing magnetic fields induces electric currents. Those currents, in turn, generate new magnetic fields, which reinforce and reshare.